Mesh analysis is a method that is used to solve planar circuits for the currents at any place in the circuit. Planar circuits are circuits that can be drawn on a plane surface with no wires crossing each other. A more general technique, called loop analysis, can be applied to any circuit, planar or not. Mesh analysis and loop analysis both make use of Kirchhoff unregistered trademark S voltage law to arrive at a set of equations guaranteed to be solvable if the circuit has a solution. Mesh analysis is usually easier to use when the circuit is planar, compared to loop analysis. Mesh currents and essential meshes. Mesh analysis works by arbitrarily assigning mesh currents in the essential meshes. An essential mesh is a loop in the circuit that does not contain any other loop. Figure 1 labels the essential meshes with 1, 2, and 3. A mesh current is a current that loops around the essential mesh and the equations are set solved in terms of them. A mesh current may not correspond to any physically flowing current, but the physical currents are easily found from them. It is usual practice to have all the mesh currents loop in the same direction. This helps prevent errors when writing out the equations. The convention is to have all the mesh currents looping in a clockwise direction. Figure 2 showed the same circuit from Figure 1 with the mesh currents labeled. Solving for mesh currents instead of directly applying Kirchhoff's current law and Kirchhoff's voltage law can greatly reduce the amount of calculation required. This is because there are fewer mesh currents than there are physical branch currents. In Figure 2, for example, there are 6 branch currents but only 3 mesh currents. Setting up the equations, each mesh produces one equation. These equations are the sum of the voltage drops in a complete loop of the mesh current. For problems more general than those including current and voltage sources, the voltage drops will be the impedance of the electronic component multiplied by the mesh current in that loop. If a voltage source is present within the mesh loop, the voltage at the source is either added or subtracted depending on if it is a voltage drop or a voltage rise in the direction of the mesh current. For a current source that is not contained between two meshes, the mesh current will take the positive or negative value of the current source depending on if the mesh current is in the same or opposite direction of the current source. The following is the same circuit from above with the equations needed to solve for all the currents in the circuit. Once the equations are found, the system of linear equations can be solved by using any technique to solve linear equations. Special cases. There are 2 special cases in mesh current: currents containing a supermesh and currents containing dependent sources. Supermesh equals. A supermesh occurs when a current source is contained between 2 essential meshes. The circuit is first treated as if the current source is not there. This leads to one equation that incorporates 2 mesh currents. Once this equation is formed, an equation is needed that relates the 2 mesh currents with the current source. This will be an equation where the current source is equal to one of the mesh currents minus the other. The following is a simple example of dealing with a supermesh. Dependent sources equals. A dependent source is a current source or voltage source that depends on the voltage or current of another element in the circuit. When a dependent source is contained within an essential mesh, the dependent source should be treated like an independent source. After the mesh equation is formed, a dependent source equation is needed. This equation is generally called a constraint equation. This is an equation that relates the dependent source unregistered trademark S variable to the voltage or current that the source depends on in the circuit. The following is a simple example of a dependent source. See also, Ohm's law, analysis of resistive circuits, nodal analysis, Kirchhoff's circuit laws, source transformation, topology. References. External links, Mesh current method, online 3-mesh problem solver.